for the second day of this demonstration. Okay, I hope you enjoyed your lectures yesterday. Yep. So today, just a minute, ma'am. I have few things which I need to sort out on my screens. So today, I would present to you three experiments. One is a laser-based experiment where we talk about laser beam divergence and spot size. The second two are the experiments from the advanced mechanics virtual labs where we talk about the rigidity modulus and Young's modulus. So yeah, so what is the laser? Right, this is what we want to start with. Okay, just to get everybody in time. Okay, so we just started and few of you are still waiting to join. I thought we'll spend a couple of minutes talking about something else before everyone joins and we get into this talk. Okay, so this is the picture of Professor Ted Mayman. He is the first person to demonstrate a laser on May 16th, 1960. Okay, and this particular laser is a ruby laser, which is the first prototype which is successful to demonstrate the laser. And those who are in the field of lasers, optics, spectroscopy would know that the history of lasers, history of optics, and the spectroscopy changed forever thereafter. Right. So this is something which we find it very, very interesting. There's a lot of good things about lasers, and the first experiment I chose is to explain what is one of the most important property of the laser, which is the divergence. Okay, so now, what is a laser? This is from Newport website, which I took it. A laser consists of three components. One is the active medium, okay, where you have the process of stimulated emission. So this is the full form is light amplification by stimulated emission of radiation. So for the stimulated emission from a matter, we need to have the matter, right? So this is what an active medium does. And to induce or stimulate the radiation, one needs to excite the matter or the active medium. That's where the pump comes into picture. So the pump is there, which is exciting the atoms, right? And then the atom absorbs, gets starts emitting both spontaneously as well as in the presence of photons which are surrounding. You could also have the so-called stimulated emission process. I'm sure you all understand what is stimulated emission. And the second part of this important acronym is the amplification, and that amplification is done by the presence of this optical resonator. So you have a highly reflective end mirror and a partially reflective output coupler where the amplification of the stimulated emission takes place. So more the round trips of the photons, more is the stimulated emission events, because there is a gain after every round trip. And so with time, you have saturation, what we call as the laser saturation, and we do have a laser output which is leaking out from this partially reflected output. Right? So this is a simple introduction of laser, right? And the most important properties which defines a laser, which distinguishes a laser with the other sources of light is the monochromaticity, divergence, and coherence. So before the advent of laser, the only choices mankind had is either a arc vapor lamp, be it mercury lamp. I introduced you about few lamps yesterday, mercury, hydrogen, etc., which gives you some light. You also have a specific color yellow output from sodium vapor lamp. Okay, you can take a neon to get some neon colors. Then you have white light from mercury, or you take the light from sun. So all these things are some sort of radiation which are called incoherent because somehow they are not related to each other in terms of phase. The different waves come out. And another property of this material, all these light sources were, they were a divergent. So one can think of a point source and light diverging out through that from all directions. Okay, so having a source which gives you a single color which is not divergent and which is coherent was unknown before the laser was introduced. And once the laser was invented, everything changed. right? Lot of applications started to come into picture, and in fact nowadays, if you look around, almost you will find the applications of laser everywhere. Okay, I don't want to get into discussion of what are the applications, but you just need to look for it and you will see laser in almost all applications. Okay, now something very important to our present experiment is the divergence, right? And so the point about divergence is the way the light emits from the, what is the kind of light that laser emits. So laser usually emits beams with Gaussian profile, right? Those who actually teach lasers or who have taken up a course on lasers would know that these Gaussian beams have this nice property of very low divergence. Okay, so we'll not go into that definite derivation, but then I just quickly introduced you a few basics which would require for our present experiments. A Gaussian beam is a beam of electromagnetic radiation whose transverse electric field and intensity or the irradiance distribution are described by the Gaussian function, which looks like this. Okay, this is how the Gaussian shape looks, and then the intensity is also varying this way. Okay, so you look at it, this particular equation, it is I naught exponential minus 2 r square by omega naught square, where omega naught square is the beam based, okay, which we call the spot size of the beam, and r is the radial distribution of the intensity when it starts from with respect to the center. So if this is the r, okay, omega is the beam spot size, and intensity is such that the way the intensity varies is like this. This particular bell shape shows that as we, if you take a laser spot and as you go towards the center of the spot, the intensity increases. Okay, so this is how we explain the Gaussian way of Gaussian distribution of the intensity. Okay, so just to digress a bit, what is the first application which mankind used to exploit the divergence is they shone the light to the moon and returned and took the reflection back from the moon. Okay, that's how they calculated the distance from Earth to moon. Okay, that's the first experiment which first major experiment which people exploited that works with the low divergence angle of the laser. Okay, now the aim of this experiment is to calculate the beam divergence and spot size of the given laser beam. The idea of beam divergence I just explained you earlier, but then why is it important to know the spot size? Okay, is it important to calculate the spot size? What do? You shine a torch, right? When you shine a torch and you have some sort of circular pattern on the screen, and if I ask you what is the spot size of the torch, you just take a scale and you measure diameter of the spot, right? That's how you say it is the spot size of the torch. Is it not the same with respect to the laser beam? The answer is no. Why? Because the way the electric field distribution happens is Gaussian. Okay, so this expression shows that the amplitude of the complex electric field is given by this big expression where you have the dependence on this exponential minus r square by omega naught square or omega z square. Okay, so this particular thing is available on the website, so you may actually look at it. I don't spend time explaining everything. The important point for us is this radial distance from the center of axis to the beam, and omega z is the radius at which the field amplitude drops to 1 by e with and field intensity to 1 by e square of their axial values respectively. Okay, so this is the most important point, this spot size. Okay, again, the intensity is the time averaged, is the square of the amplitude divided by 2 neta. Neta is the impedance, wave impedance. Okay, so if you do this, this is what you get it. And so whatever I showed you earlier, I just showed the basic expression on which it depends. Now, if this is the true expression, I of r of z equal to I naught omega naught square by omega z whole square. Okay, exponential minus 2r square by omega z square. Okay, which is similar to omega of z is how the beam is varying with respect to the center. Okay, yeah. Now, this picture explains you why it is important for us to measure this process. Okay, so what our eye perceives is, if you look at it, if you understand our own organs, the eye responds in a logarithmic fashion. Okay, so if you change the intensity, a photodetector would respond linearly, meaning you take a plot of the photocurrent which comes out of the photodiode or photo in the photodetector, and the intensity, as you vary the input intensity linearly, the photocurrent varies linearly. And that's how you call the photodetector as a linear detection. However, our eyes, just like our ear, is a logarithmic device. So we do not perceive things in a linear way. We perceive in a logarithmic way. Okay. So if I find that the intensity is doubled, it means the intensity actually gone by an order of 2, 10 power 2. Okay. This is the idea of that's why when we look at our eye, when we see the beam spot, our eye cannot perceive, cannot really understand what happens beyond the region where the intensities are very low. Okay, so if you look at it, I just shown you a very graded way of the spot, and then this spot is having a Gaussian distribution such that the 1 by E part is enclosed in the circle, and beyond that the intensities are so low that probably our eye cannot see. Okay, and second point is, even if you take a strong green color where our eye is more sensitive, what happens is the center part is so bright that we will not be able to see the periphery of it. So that way, the end part, the periphery of the beam spot is very hazy, and if you take a simple scale to measure the spot size, it is not the same. Furthermore, when you focus the light, when you focus this laser beam, it doesn't follow the way we learn in our question in our geometric optics. So in a geometric optics, we see that you have if you take a lens and you focus the beam, it nicely goes through the focus. Okay, so you can just draw a straight line and you put a dot at the focus. So that's how we learn and we teach the geometrical optics. However, the way the Gaussian beam focuses is not the same. It doesn't really focus to a spot. It has a certain beam base, what we call the beam base. Okay, and all those things require some measurement technique to really find out what is the spot size at the focal spot. Okay, so all these things require scientists to find out ways to look at the plan out an experiment that really tells us how to measure the spot size. Okay. So the two beam parameters are this. One is the beam divergence. The light emitted by the laser is confined to a rather narrow cone, but when the light propagates outward, it slowly diverges and fans out. So it just goes out, but it takes a lot of distance to actually really diverge. Right? This is what it is. For an electromagnetic beam divergence is the angular measure of the increase in the radius or diameter with distance from the optical aperture as the beam emerges. Okay, so if you take two spots, yeah, we take two spots, two distances. So this is the spot size at this distance. This is the spot size of the distance. Keep in mind when I talk about spot size, it is the diameter where the intensity goes down by 1 by e square. The diameter where the intensity goes down by 1 by e square. So in principle, you might have some more intensity here, but it is less than 1 by e square. So what happens is you just take the circular radius with where the intensity drops down by 1 by e square and you plot it with respect to distance, and that's how it varies. Okay. So this, if you say d1 is the size, spot size at distance 1, d2 is the spot size at distance d2, then the d2 minus d1 and the theta is how the spot size is varying with respect to this particular axis. Okay, this is how you design the beam divergence. Okay, and second important point is the spot size. I think I spent a little amount of time to discuss the spot size. The spot size is nothing but the radius of the beam itself. The radiance of the beam decreases gradually at the edges. Okay, so that's why the edges are hazy. The distance across the center of the beam from which the irradiance becomes equal to 1 by e square of the maximum irradiance is called the beam diameter, or the spot size omega. Okay, this is what it is, right? So if you take this guy, so this particular length parameter is equal to this length parameter, and so as the beam diverges, so this length parameter keeps on increasing like this. That's how it fans off in this direction. Okay, just look at it like this. Just This is the spot size, and here at far it just increases spot size. Okay, so in this experiment, we study both spot size and the beam divergence. So without, so even before I actually show you the experimental setup, if I want to know the beam divergence spot size, all you need to do is take the detector at a certain distance d. Okay, measure the spot size, learn how to measure the spot size, and go a little far, measure the spot size, and then use the information about the spot size to get the beam divergence. Okay, so the important experiment here is to actually know how to measure the spot size. That's what we start with first. Okay, so you need to arrange the laser detector in optical bench parameter, the laser is switched on, and these are the various procedures which you can find there itself. Okay, so the important point is this: the if you fix the distance of the detector from the laser source by adjusting the micrometer of the detector, move the spot. So you put a detector at a certain distance, okay, and then if let's say this is the detector and you move it along this beam spot, you can in principle measure how the intensity is moving. Okay, so this is what we do here. Okay, so the way we do further the divergence is to repeat it at different distances and then note the points in the graph where the intensity 1 by e square of the maximum intensity, say it as IE. Find the micrometer distance across the beam corresponding to these points. For a pair of distances, detected distances Z1 and Z2. Okay, half of this distance is known as omega 1, omega 2, or W1, W2, and the divergence in spot size can be calculated using the equations, which is there online. Okay, so this is the experimental setup. So all you get to do is to okay to choose various lasers. Okay, you have krypton, helium, neon, argon, and again, as I say, it's a beauty about the virtual labs. If in the lab you want to buy these three lasers, you need to spend close to 30 to 40 lakhs, correct? Where here it's free for you, right? So you can, in principle, choose three lasers, okay, just to see how the colors change. Okay, and here I have shown you how the laser looks there, setup looks like, and this is the arrangement where the laser is there somewhere outside through the screen like this, and laser is on. When the laser is on, this is the detector which sees the laser, and this is the spots of the detector which I just zoomed in. Okay, so the spots is zoomed in, and if you look at it carefully, there is this dark center and a very weak periphery. Okay, which brings to that. So all we do is fix the detector distance. For example, it varies from 50 to 200. Fix the distances, and as you fix that end, you move the detector. So all you do is you move this guy across. This micrometer does that. It moves across, and then you see how the intensity is changing. So the photocurrent which is coming out of it is measured here in terms of microamperes. Okay, so with respect to the distance or the position of the detector, the distance, the current varies, and so you can see that with respect to the distance, the current would actually vary in a okay in a Gaussian way. Okay, this is exactly what the experiment we do. And if you do not want to take the data, if you're lazy, just want to do quick experiment, you can also show result, and it will show immediately. If you show graph, it shows. I just logged in, but it is logged out before during the class. Okay. So theory is there, procedure is there. You can evaluate and simulate it. So I will not repeat everything what I showed yesterday. on this. Come on. Yeah. There we are. So yesterday I have realized another aspect of this VLAPS. You do have the option of choosing this button for making it full screen. However, when you put the full screen, there is a limited input capability, so you may not be able to do it. Okay, so I hope you can do something here. Let me just go to helium neon output and I start the laser. Okay, so when I start the laser, you have it here. You see this point. Okay, so let me look at this particular distance Z0, and I use this detector to actually move. Okay, and just move it. As I move, I see this guy moving around. So because it says not visible, sir. Oh, sorry. Maybe you're not able to see it. Is it visible now? Please confirm. Is it visible? Okay. Is it visible now?
Yeah.
Yes, yes.
Have you displayed anything, sir?
Yeah. Looks like I did
Yeah,
not
now,
share this.
now it's visible.
Yeah. Okay, it's okay. I got the point. Yeah. Yeah. How about this?
It's good.
Okay. Yeah. So all I did is I started the experiment with this experimental setup. Okay. So you do have this. If you take this simulator, you can choose this option here where you have a full screen, and you can start the full screen so that the entire thing is visible. Okay, I have chosen krypton, helium, and neon argon. I chose the helium laser, and I started the laser. Okay, so you see this guy, very bright. So what I need to do is the following. Is there still any problem? Hello? Is there any problem? No. Okay. Yeah. Kindly mute because I'm getting a lot of distance. Yeah. So I just choose this distance Z0 equal Z equal to 50, and I move the detector's position. Okay. So I move it, I move it, I move it. Okay, now I know what's the problem. Okay. I can say show graph so that we know what is where it is coming. Okay. And I can move. Slowly moving. Keep note about this. As I move this detector distance, this micrometer is also changed. Okay. So I move, I move, I move. Because I moved very fast, this entire thing has come very quickly, and I can say show the result to see what is the beam based. And the spot size at this particular beam at this Z equal to 50, which is 0.404131. Okay, now there is not fun. There is no fun here. So all I do is I stop. I won't say show result. I can just go back. Okay, and then know that it starts somewhere here. Okay, it starts somewhere here. So I can just come here. So till here it is all 0. Okay, and then you can we can just click here so that this particular button is activated, and use left and right buttons, and I can show it here. Okay, the way it is here. So if you carefully observe the main scale reading, it is somewhere close to 1.5 and matching at 40. So 1.54. It's in millimeters. So 40 microns, 0.01 would be the least count. Okay. Then you see as I go further, every time I click one, it is changing by one. Okay. So I click. Yeah. That's how you can take the entire measurement. You can just note down these numbers in your rough notebook, in your observation notebook. Don't ever use rough notebook, it's an observation notebook. And then you can go to some plotting software to actually plot and then do the measurements of 1 by e square of that point and you get it. So this is what we do at this z equal to 50. Now I can go further and see how it looks when it goes to z equal to 200 centimeters. When it goes to z equal to 200 centimeters, automatically there is some beam divergence we are not able to see because we are at our visible ray, at our position. This guy is very far and we don't get to see the spot change. So we repeat the same story here. Okay, I can just slowly come here, see where the 0 is there and finish it. Okay. The same thing here. So one good point which I want you to notice is that within this, when it is at z equal to 50, we had to go almost till 1.45 to reach that point where it is maximum. Okay, where it starts picking up. However, in this case, it doesn't require all these things. It just starts showing at much earlier. So even at at the very part itself, you start seeing the signal, and then the height is very small, meaning to say that the energy of the beam is distributed over a big spot size. Okay, energy has to be conserved, right? So if I have a beam spot size of this, all the energy is within this circle. If the spot size is big, now the energy is also distributed through the entire spot size, and that's how the intensity at the maximum or the center has drops down and the energy is distributed towards the periphery. Okay, this is the second good idea which we can see. And again, all I say is that you can just choose here and then click and put your cursor here so that you can see the zoom part here somewhere in this point. Okay, and then you can vary. As you vary, you start seeing it. Yeah. So I just stop here. I think you got the experiment, the idea of the experiment. Yeah. Let's go to our PowerPoint. Right. So I have done this. In fact, the same thing we did yesterday. And at z equal to 50, we took all the readings. Okay, exactly the PSI, HSI total. What is the distance traveled and the current which we see, and you plot it. So this is the experimental data. Imax is here, 0.0018 milliamps. Calculate what is 1 by e square value, which turns out to be there. Okay. So in fact, because it is simulated, it is much easier. There is always a point which you can directly take it. Okay. So there is 1 by e square value already measured in your experiment. And then you see the distance between this point and say that your spot size is exactly 0.04 millimeters. And this number matches well with what is already shown you in the show result part. Okay, and then here you have this matching with the experiment show graph data, which is here. Okay. Similarly, we do the same thing for z equal to 200. Expectedly, here the extent where the energy is concentrated is limited, and so we have very few points. In the next slide, you see there are a lot of points. Okay, so energy is distributed over long point, meaning the beam is expanded pretty much. Okay, it's diverged to a good extent, and that's all. You have this particular graph which shows like this. Again, you can get very good data because a lot of points are connected. See the maximum, calculate what is z square value, find the distance, omega 2, you get 0.16, and this matches well with the show graph, right? So now all you have is, you know the distance is d1, d2, you know what is omega and omega 2. So I would leave the assignment to you to calculate the beam divergence and cross check whether you will still get the same thing what we got or what the simulator gets. Then you may repeat the experiment with argon ion laser or krypton laser, and that's all. You get expertise over this particular experiment. Okay, I hope I convinced you what is the very beautiful property of the laser, and this is how it comes. Okay, so we move now to the next two experiments, which is rigidity modulus of the suspension wire of a torsional pendulum and omega Young's modulus of the given material bar by non-uniform bending method. So these two are available in the advanced mechanics lab section of the physical sciences portal of Amrita website. Please check it out. Okay, so the idea of this torsional pendulum experiment is to determine the rigidity modulus of the suspension wire using torsional pendulum, and second, to determine the moment of inertia of the disc. So this is a very favorite experiment to, it's one of the most common experiments we do at the first year BSc level. Okay, so what is it? You all know pendulum is eventually something which oscillates, right? So here, this is what is oscillating. You have a disc suspended to a wire, and you let the disc oscillate about this axis, and we do this experiment to find the rigidity modulus of this particular wire. Okay, so in the experiment you find that there are a lot of different wires available, so you may actually look at the rigidity aspect of that wire. Okay, so I don't think I need to explain you what is rigidity modulus, etc. I'm sure you all know about it. So just to give the basic theory, the time period of the oscillation is 2 pi root I by c, where c is called the couple per unit twist, 1 by 2 pi neta square r power 4 by neta r power 4 by L. Okay, by L, yeah, where L is the length of the suspended wire, R is the radius of the wire, and I is the moment of inertia of the disc. Okay, the rigidity modulus of the suspended wire can be found by this formula, eta equal to 8 pi I moment of inertia of the disc, L by r power 4 t square. Now we all know what is the moment of the inertia of the disc, which is mr square by 2. So we can just calculate it as for the mass. If we do not want to do, we can also use this experiment to find out from the time period. So all this experiment does is rotate this guy, give an oscillation, give a small twist to the disc, let this disc oscillate, calculate the time period of the oscillation, and then plug in the values to get the required quantity you are putting in. Okay, so this is the basic theory which I will just zoom through. If you assume a rigid body is suspended for a wire, from a wire attached as its top of the fixed support, as you see, the twisted wire exerts a restoring torque on the object that is proportional to the angular position. Okay, that's how you have the oscillation which is happening. The restoring torque tau is equal to minus kappa theta, where kappa is the torsion constant of the support wire, and the Newton's second law gives the torque equal to I alpha, and that's how you can bring in the concept of moment of inertia. Okay, so d square theta by dt square equal to minus kappa by I theta. So you need to look at how the angular position is varying with respect to the angle, with respect to the time. Okay, that's the acceleration, angular acceleration. D square theta by dt square is the angular acceleration, right? This is the entire story of it. So one can look at the rigidity aspect of it just by twisting it and seeing how far you can get the twist. Okay, and then it's not just how far the twist, because if you look at how far the twist goes, you will reach a point where the wire breaks. So you do not want to go there. You want to use some property of the wire in order to eventually see how far the property, how far the really the wire can be twisted, and that's how you can get the rigidity property of the wire. Okay, so this is the experimental setup. Okay, simple. You have a wire suspending the disc, right? So the part one of the experiment is to determine the determination of rigidity modulus using torsional pendulum alone. Okay, so without placing any external mass on the disc. So those of you who remember doing the experiment will know that there are two parts to it. One is you do without any weights on it. Second is you start putting weights on it. So when you start putting the weight on it, you find moment of inertia using torsional pendulum with identical masses. That's the part two. Okay, so these are the things which this experiment allows you to choose. It allows you to choose identical mass, a disk mass, disk radius, wire length, which is what it is here. So the suspension wire, you have a lot of options, copper, brass, and so on. I'll show you in the main thing. Okay, then the identical mass position, no cylinder, which means there is nothing on this. Then you can start putting disk mass. Okay, you can start adding masses to it, and you do have option of changing the disk radius and changing the length of this suspension wire and also the width of the radius of this wire. Okay, so you may be able to simulate everything whatever you can in order to really understand how the wire changes. Again, I find this particular experiment is a good addition to our teaching. When we teach simple mechanics into the first year BTech or first year BSc, okay, this particular experiment can allow us to simulate what happens when the thickness changes, what happens when the disk radius changes. So all these things come up. Okay. Yeah. So now comes the point of what happens when you put in D1. So you can use, I'll just show you in the main thing that here in this point, you can fix certain things, and whatever you do, you can have the information about it in this point. At D1 position, you can change, you can start adding masses at this. So this is fixed. Okay. So value of D1 is 4 centimeter, sorry, 4 centimeter. And the second position is D2 position, where the cylinders are put at the periphery and then they are separated with respect to each other by 4. So one is 1.5. I'm sorry, earlier D1 is 1.5 and D2 is 4. Okay, so this you do not have choice. First is it allows you to put the two weights next to each other, separated by 1.5 centimeters. And then the second position gives you very far, which is 4 centimeters apart. Okay, 1.5 and 4, and then you get to oscillate. Okay, so the next I will show you what is the experimental data. Okay, so let's stop this guy. And go to the Chrome. Okay, so this again, I got it here, rigidity modulus of the suspension wire of the torsional pendulum. You have everything here. Let's go to the simulator. I hope I don't need to do it. Thanks, thank God. Yeah, as you see here, this particular experiment doesn't allow us to have all the options once in the full length mode. So I will avoid it, but I'll just show you to begin with in the full screen mode how it looks. Okay, so as you see, you can choose various options: copper, brass, bronze, cast iron, zinc, aluminum, cast steel. So these are the various material composition materials you have. Okay, so the first experiment is no cylinder experiment, so you don't put anything on it. All you do is you have the option of show stopwatch and show time period. So you just give a click to this for it to start oscillating. Okay, now if you look at it, the time period is 2.8596. The time period is 2.8596 seconds. So this is what I got because I allowed to show the time period. Okay, if I don't show, you can start using the way we do actually experiment in the lab, where you start and you calculate the time period. Okay, so the way we do an experiment is in the real life is you let oscillation start and you count about 10 to 15 oscillations or 20 oscillations. Excuse me, can you please stop talking? I cannot concentrate. Hello? Yeah. Yeah. So here you can start counting the oscillations and then you take the mean of it and stop after certain number of oscillations to get the time period. Okay, otherwise we can also do this simply just show time period so that you can also cross check your actual experiment with the time. So this is a simulated one, so you don't really get to choose the time period. You cannot give a big twist or small twist. You just give some twist and you have this time period. Okay, so I stop it. You have the number of time period. You have all the information. So plug in the formula. I'll show you the formula once we go back. Here I just demonstrate. The next is to see what happens when I put in the D1 position. I have these two masses. Okay, I can keep on increasing the mass from 5 grams to 50 grams. Okay, you see this? And this is in the D1 position, meaning these two are 1.5 centimeters apart. Okay, now with this, I click and let the time period change. Okay, so now with the addition of these masses, the time period is changed. It is now 2.8908 seconds. You like to be practical, stop this guy and start. Okay, now stop after you count 10 or 20 oscillations and take the mean of the time period, and that's how you get the entire time period. That's exactly what we do in the lab. Okay, the next is stop it and let it go to the D2 position. Okay, and click. Now the time period is increased, of course, because the weight is increased, and now the time period is 3.0424. And then with this time period and the value of D2, T1, the masses, okay, the disk mass, disk radius, suspension length, suspension wire radius, you can actually start plugging in the numbers to get the rigidity modulus and the moment of inertia values. Okay, so I stop here and go back to my PPT where I actually sat and measured the things. Yeah, so this is the first one. Second one, okay. Yeah. The two equations are here. Moment of inertia I naught is given by this formula, 2m d2 square minus d1 square, t naught square by t2 square by t1 square. Okay, so t naught is the time period where you don't put any mass, that is the no cylinder measurement. D2 is when the masses are at the D2 position. T1 is the time period when the masses are in the D1 position. D2 is 4 centimeters, D1 is 1.5 centimeters, m is the mass of the disk. And so you can, in principle, obtain the moment of inertia of the disk using this entire formula. Similarly, you can also use these numbers to get the rigidity modulus of the wire. And we have done this by changing this length of the wire, radius of the wire, the time period. So as you change the length, radius, the time period changes. Similarly, the moment of inertia should not change. Okay, and to keep it constant, obviously, if it changes, then something is wrong, correct? So you should get similar numbers, and in fact, you end up getting the same number. Again, keep in mind this is simulation, so the chances of error are very little unless they want to measure something with wire calipers where because of our own parallax error we make mistakes. Similarly, for this we have used these numbers to get the rigidity. Okay, and then if you look at it, the average of this entire thing, the mean rigidity modulus turned out to be 1.5164 into 10.9 Newton per meter square. Okay, I can do the back calculation and find out from simple. So this is by putting this. I can also find out by using T naught square, T2 square, and T1 square values, and back calculate what would be the moment of inertia. And if you look at it, it is similar to what we have started with, which is 0.002693 kilogram meter square. Okay, so this experiment allowed us to actually calculate the rigidity modulus of the wire, and also if you know this rigidity modulus of the wire, you can back calculate and get the moment of inertia of the disc. So this is the example of torsion pendulum, and this experiment is something which we always I find in all the labs across the country in the first year of BSc or BTech. Okay, so it's a very useful handy experiment to learn from virtual labs. The next experiment is the Young's modulus of the given material bar. Just like how rigidity modulus tells us how rigid the material is, Young's modulus tells us how stiff the material is, right? So in this experiment, we find the Young's modulus of a material bar, here in this case a scale, by the so-called non-uniform bending method. There is also another method called uniform bending method. I would ask you to please go back and try that out for the same bar and see if you get the same number. Okay, what are you measuring now? Okay, so this is the aim and apparatus to find the Young's modulus of given material bar by non-uniform bending using pin and microscope method. The apparatus is, you take a pin, microscope arrangement, a scale, vernier caliper, screw gauge, weight hanger, etc., which is very understandable. So the way to do it is this. Okay, this is how you do it. So you take a scale, okay, you put a pin right at the center and suspend a weight here, somewhere here. Okay, right underneath it. So what happens is, you need to make it stand over some fulcrum. So here you have two, okay, weight hangers or the knife edges, which is there. And so if you keep changing the distance between these two, the amount of bending will change. If this is very close, it won't bend much. If it is very, very far, these two, the bending is too high. Okay, now as you change the distance between these two hangers, okay, the knife edges, the position of this pin changes. It goes up and down depending upon the distance between these two. And all you do is to have a traveling microscope, which is this, and see how much the height has changed with respect to either the weight or the distance between these two. And then using all this information, you can plug in the formula and get the Young's modulus number. Okay, just to give the theory, Young's modulus, it is the ratio of normal stress by longitudinal stress given by this, and it is basically a measure of how stiff is the material. Okay, so the non-uniform bending method using pin and microscope, I have explained you what it is, right? It is supported symmetrically on two knife edges and loaded at the center. The reason why it is called non-uniform bending is simple. Okay, if you look at it, the way, if you take the entire meter scale, okay, the bending is not uniform. If you take a small portions of this, if you take this is L and you take a small length scale, which is delta L, let's say the length scale is just a small piece of this, and you keep seeing how much of stress you introduce at each of the length scale delta L, it is not uniform. Okay, so that's how, obviously, that's how the name non-uniform came. Okay, similarly, if you choose to put the weights in this point and this point, then what happens, this guy would bend like this. Okay, and that's where we have the so-called uniform bending. That's the next experiment which you may try out when you go back. Okay, so this is the non-uniform bending using pin and microscope. Okay, the important point is y is mg L square, L cube by 48 LE. L is the length of the knife edge, L between those two length between the knife edges. Okay, E is the depression in the bar. This depression you get by seeing how much the pin is going down, because when you put the weight, it is going to bring down the entire weight down as you increase the weight, and such so the depression happens. So either you change the depression because of the mass loaded for the depression. By changing mass, you can get this E change, or you can change this L. Okay, change the length between the knife edge to get this depression. Either way, you get what is the Young's modulus, and for the rectangular bar, the L is BD cube by 12. You can get that number, and substituting all these things, you have this actual y equal to mg L cube by 4b d cube, 4db d cube by and e. Okay, so this number is this formula is what you're going to plug in based on the various quantities you measure in the experiment. Okay, this is the procedure of the simulation. Okay, so you get to choose all these things. This experiment allows you to choose the environment and material used for the experiment. So here you have the option of choosing what happens if you put the metal, if you put the meter scale on Earth, on Moon, on Jupiter, on Saturn. Okay, you can have fun. Just like that, you can also have fun with respect to the material of the metal of the bar. You can use a metal scale, or you can use a wood scale, and so on. The weight on the hanger can be changed. The breadth of the bar can be changed. Thickness of the bar can be changed, and also one can change the adjust the distance between the knife edges by this. Okay, if you're too lazy, you can just say to flow result, and you get the y. Okay, so this is the experimental setup, and this is what I have taken snapshot when by putting the maximum load of 500 grams. I put all the available masses around and see how much of depression I can get with this. Okay, so that's how we get it, and you can also reduce the mass. Okay, I'll just show you the observations later once I finish the showing this particular experiment. Okay, let's go to full scale bar. Now, as you see here, this is the position of this particular pin at the distance 50. Okay, the knife edge 1 at 45 and knife edge 2 is at some point, and you can use this focusing knob so that you can get a very clear view of this pin. You look at it, this is the crosshair of the traveling microscope, and then to look at the height, if there is a change of the pin, you can play with these two screws. Okay, you can play with these two screws to get it. All I do is you have Earth, Moon, Uranus, Saturn. So different, different environments would have different acceleration due to gravities, and that's how the way the modulus changes also changes. Okay, I have taken the entire. I keep increasing it. Okay, keep increasing it. I can choose length very high. I can choose somewhere in the middle. I can do whatever I like. 2 centimeters. I can take the breadth. Okay, thickness you can have as much as you want. I'm just choosing something in the center, and then the distance you can change. Now keep observing this as I change the distance between these two knife edges. Okay. Again, the one question to all of you to think before I answer is, now I know that my pin is going down, correct? As I have very high wave mass, and as I move this guy apart, I know that there is a depression forming. So in this case, my pin should go down. But here, why am I observing the pin to go up? Okay, that question typically it's the common question we ask for the Viva to an entry level student. Okay, the reason is simple. Our microscope is seeing an inverted image, so what is going up is actually going down. That's the only answer. Okay, so what I do now is I can keep here and then vary. Okay, I can keep clicking. I can keep clicking. I can keep clicking, so that I can bring the pinpoint at exactly at this cross. Now, how do I start studying? How do I take the measurement? This is where I click here. Okay, can I show you? I go here in this position on the scale. there's a plus, I click on the plus and then you see. Okay, so now let me just go with the main scale reading so that I can avoid the time. This is somewhere around 6.5. Yeah. Now if I reduce it, okay, so can go back this way to the original position. Then look at this. So this is now at 5.5 almost. Okay, so about 1 centimeter difference we have with the maximum distance possible, and you can take at different knife edge distances. Okay, you can have the option of keeping the knife edge fixed and changing the weights, or you can do the other way. You can do this, you can do that. Eventually, start filling up these numbers, masses L, B, T, and finally get the Young's modulus. Okay, this is what you get it. So I stop sharing and show you my results. So this is the value of MSD, number of divisions, least count, what we can calculate. Okay, then these are the various points to be filled as per the experiment. Okay, these are the things to be added and the result can be obtained from this. Okay, thickness of the bar, all the things you noted down. Always make it a habit, even when you work with virtual labs, take a good notebook and write it. Maintain the observation notebook. The present generation of students are very much used to directly typing in the computer or any of their softwares. Please tell them that no matter it is an old method of doing it, whatever you record in the notebook will stay till you actually burn it or throw it or a cow or a buffalo chews it. Otherwise, the book is dead with you, more or less. Okay. If they directly record it on a computer, there is every chance that the computer may fail, the laptop may crash, and it may be lost forever unless they make multiple copies. So another point is always a book is always handy. So observation notebook allows us to start writing whatever we like. We can actually make measurements. We can record our remarks. We can record our actual what we see. Everything can be written, and later on, after 2 years or 3 years, one can actually go back and see what we understand from the experiment. So these are the things which I always tell my students. So as faculty, it's our job to still sensitize the students to write proper record, proper observation notebook. Because later on, when they come to the eventual PhD's level, a 5 year, if they don't get used to writing the observation notebook, after at the end of the 5 years, when they start writing the thesis, they are lost because they do not know what they've taken when. Okay. Yeah. So this is the small thing which I thought I will impress upon many of the new faculty. So these are the things which we did. I just fixed the distance and varied the mass. Okay. And took the eventual Young's modulus, which is here, which is 1.14 10 power 10. And in fact, if you click show results, this is what the Young's modulus of the meter scale made up of wood would be from the website. Okay. So to summarize, I have taught you or I have introduced you 3 different experiments today from the virtual labs. One is the laser beam divergence and spot size. Second is the rigidity modulus of the suspension wire of a torsional pendulum. Young's modulus using non-uniform bending method. As I mentioned to you, there is another way of doing the same experiment, which is called the uniform bending. Okay, so you may actually try out these things, right? So I like to acknowledge Professor Padma and the organizing team from the invitation. Okay, thank you, ma'am, for this wonderful opportunity. Along with this presentation, which I need to do, I studied myself again. And then it's not me alone which I did. My students helped me, okay, especially Vaibhavi and Chingappa. Okay, I should mention because you may think that I did all the experiments, I took all the measurements. It is wrong. I have asked some of the help from these people. Okay, so Vaibhavi helped me with respect to the laser experiment and yesterday's one experiment. Chengappa did both the in mechanics experiments. So thanks to those them. Okay. Now, if I still have time of 5-10 minutes, I thought I would digress a bit and explain a little bit of what I do. Please, may I have the permission, please? May I have the permission now? Yeah, just 5 minutes. I will just digress. Okay.
Yeah,
I thought
carry on, sir.
I would just use this opportunity to show a little bit what I do. Okay, so my key area of my research is the emerging trends in organic photovoltaics. I will not bore you with all these things, but just to impress upon you what is the latest trends that is happening in organic solar cells. So if you look at all these pictures, this is a building where you have the colors which you change. And if you look at it from far, it may look as if the windows, the windows or the glasses which are fitted here are of different tinges, but it is wrong. Actually, these are all the big coated, solar cell coated windows, which can generate their own electricity. So instead of using a normal glass plate, which is, if you come to Hyderabad and you look at high-tech city, you see all these buildings with glass, with so much of heat, etc., generated inside and so much of energy wasted because unlike if in the West, normally the way in the West people try to conserve energy is by using these glass windows because they use the sunlight to heat up their interiors. It's a cold place, and if you go northern hemisphere, it's a cold place, and the interiors are heated up because of the sunlight. So they are using the nature to actually to their advantage by using the glass. We, on the other hand, copy them, and even though our outside is very hot, we try to have the same glass plates, okay, and we get baked inside. And to make sure that we are not roasted at the end of the day, we use a lot of air conditioner to cool it. So it's a irony and pity, but then that's how it is. So now the trends are changing, and people are trying to use the color, the facades of these buildings by replace this with solar panels and then to get the electricity. Now, when we talk about solar panels, the first thing we think about is the silicon solar cells, which are black and black and non-flexible, and they are think about the liquid panels. Now, the organic solar cells have changed that aspect, right? You can, in principle, have solar cell which is flexible. If you see this, it is deposited on a flexible substrate which can bend it but still let it work. Okay, so this is having separate colors. This is the idea of the printing a solar cell. So you can actually print roll to roll, just like how you print newspapers. So all these things have gained a lot of importance in the present day world. Okay, and so the organic solar cells, organic photovoltaics are now emerging as a nice alternative for energy requirements. Before that, so I will just give a little bit of more things about it. Okay, so we start from the grand challenges of mankind. Many of you who are taking this FDP are, I'm sure, early career people who might have just finished your masters or just finished your PhDs or just starting your teaching. Okay, so we have a lot of life to contribute to the mankind, and it is important to actually learn what are the various challenges which we feel. I just listed out this top 10 problems. If you look at it carefully, everything is what is hampering the growth of everyone, everyone across the entire world, not just our country. And the important underlying solution or the panacea of all these things is sustainable development. Okay, so this is the medicine which can solve all the problems if you can really work towards sustainable development. Okay, it's not just solar cells, something. Whatever we do, whatever we innovate, it should be sustainable. It is not something which we use up what is available and to do something new. We should be able to use up and also generate so that it can be there forever. It's called sustainable development. Okay, so just to understand what is the world marketed consumption, this is how the world is consuming. Okay, excess joule per year is 10 to 18 joules per year, and the projection says this is done sometime around 2010, right? And so the projection is that it is going to go up with years. Obviously, as the population grows, as the technology grows, the requirement of energy also grows. Okay, so there is a lot of impact on the world market, on the energy consumption. So one needs to find ways to generate this energy. Okay. Now, if you look at the various fossil fuels, look at the crude oil, natural gas, high quality oil, coal, etc. They are there. They are able to generate. Right now, we have lots of fossil fuels left. Okay. So, in fact, we have 36,600 exajoules of fossil fuels still available. It was available about 13 years back. Maybe now a percentage would have gone bad, but still, this is sufficient to cater for next 20 to 30 years of the requirement. Okay. However, as we know, fossil fuels are something which are by name fossils. You have this happening or generating over the last billions of years or billions of years. And if you use it up, you need to wait for next million or billion of years to actually generate them back. Okay. So you can use it, but you cannot generate them. And so it is projected that, so this is the latest one, this is the last year's one, this particular trend, and it is found that the coal is what is going to do for some time, but the oil is going to come down by 2050. Okay, oil, gas, and eventually coal. Whatever happens by 2100, we are lost. Okay, so it is important that we need to look at the renewable power sources. So as per the latest trends published by international energy agencies, renewable power capacity is set to expand by 50% between 2019 and 2024, which is the next 5 years by solar photovoltaics. So keep in mind, this is pre-COVID calculations, so things may change because of COVID. COVID is not changing the requirement of renewable energy power capacity, it's just changing the way we are pursuing the experiment, pursuing the research or pursuing the technology. Okay, so it's just last 6 months there is a stall, so hopefully we will go to pick up later. The installation of solar photovoltaics on homes, commercial buildings, and industrial facilities is set to take off over the next 5 years, transforming the way the electricity is generated and consumed. Okay. So this is the futuristic way for the next 5 years. It's from International Energy Agencies. If you look at this, is how the gigawatts are generated. Okay, so solar photovoltaic is what is expected to have the major contribution for the next 5 years compared to the other ones. Of course, everything is required, and that's how we grow together. Okay. In fact, solar power in India is fast developing industry. The country's solar installed capacity reached 35.12 gigawatt as on 30th June 2020. It is not far, just 2 months back. And interested people can just type solar power in India, look at the Wikipedia page to understand all the beautiful work our country is doing. In fact, our government is really putting a push since last 10 years. There was a mission which started in 2011, and we are progressing very much. We're making rapid strides towards this direction. Okay, now there is something problem with this. Is solar energy always green? In fact, the answer is no. Solar energy isn't always green as you think. When I say green, it is not the green color, but it is the impact it has on the environment. So do cheaper photovoltaics providing solar energy come with a higher environmental tax? Again, yeah, you may just note down this keywords and type it. There is a free article available on IEEE Spectrum. This is what I downloaded, and you'll see that it is not, and there is a huge carbon footprint which is being developed because of this solar cell. In fact, if you look at this x-axis, you have the solar panel type, which is single crystal, multi-crystalline, silicon ribbon crystals. All these things are based on the silicon-based solar cells, which is prevalent everywhere. All the solar panels which we see are silicon-based, and you see that these silicon solar cells are giving a lot of carbon footprint. Okay? Too much of carbon, because the way silicon solar cells are made. Okay? It's a big talk, but I will not talk about it. Okay, you might just start searching from it. I want you to look in. Now everything is free online. Just keep typing, and you see everything is available. Please know that silicon solar cell has a lot of environmental impact. Okay, therefore there is a huge requirement of alternate energy technology that are eco-friendly and cheaper. Okay? This is where the next generation of solar cells come. So for a PV technology to satisfy the sustainable criteria, it should be economical, made from abundant resources, along with lowest environmental impact. Okay, Ashtadigbandhana we say, right? This is what it is. Yeah, everything is stopped. So to get, one needs to follow this strictly in order to get it, and that's where the organic solar cells come in. Okay, why organic solar cells are important is because of all these reasons I just mentioned about it. You do have various colors. It is cheap. You can print it. You have roll-to-roll processing. Okay. You can see, you can just use it. You can coat it on some tables or chairs or whatever. You can have it on bags. You can deposit on umbrellas. You can deposit it on your bus stands to just generate electricity sufficient to charge your mobiles, etc. And also there is a huge importance in the building integrated BIPV photovoltaics, where I just impressed upon you the requirement of changing the facades with solar cells. Okay, so these are the requirement why emerging photovoltaics are coming up, and in particular, organic solar cells fit the bill. How? Organic molecules-based energy conversion devices have gained a lot of importance, interest as an alternative form owing to the possibility of low-cost fabrication procedure, ability to print them on flexible substrates, engineering at molecule levels to tune the band gap and charge transport characteristics, and a potentially less hostile environmental theory. Okay, just like how our pharma industry is able to meet the requirements of drugs by large scale manufacturing of the drugs or the molecules. If we can bring it to the we can try to design those molecules which are used for conversion and can really generate lot of dyes, lot of molecules which can solve our energy. And also these technologies involved include organic solar cells, dye-sensitive solar cells, hybrid where you have perovskite and quantum dot solar cells. So all these things is the current technology. I will not tell everything in detail, but please look at it about organic solar cells. You get to know that why I'm saying, you get to understand why I'm saying all these things. Important is the low cost when it comes to the manufacturing. And typically organic is expected to be organic. This is how we have a lot of fetish for organic food products. Okay, because you expect it to have less environmental impact. You would expect the same with the soap. Okay, and now we are doing really good. In fact, if you look at it, this is the best research cell efficiencies which is come out, which is provided by National Renewable Energy Limited. Okay, it's a US-based laboratory which keeps publishing every 6 months or every 3 months what is the latest development in the solar cells. If you look at it, I just removed the lot of the other solar cells which is there. The earliest solar cell is dye-sensitive solar cell, which started in 1992, and then at the moment the best are the perovskite solar cells, which is the green circle with a red circle with a yellow dot. Exactly it is. If you look at it, this guy started around 2030. Okay, so this particular technology started in 2013, and within 7 years we are there at 25.2%. And if you look at this number, 25.2%, it is close to the single crystal solar cell, silicon solar cell. So organic photovoltaics is actually giving competition to the well-established silicon solar cell. Of course, there are a lot of opportunities in this field because silicon solar cell is what is being commercialized and used around everywhere because industry is able to put in money. When will the industry put in money? When it knows it will get back more money. Correct? So silicon solar cell technology is most mature and it has stood the test of time since last 30 to 40 years. Whereas all the solar cells, no matter how good they are at the lab scale, it needs to be pushed to the market level, which means a lot of effort has to be put in from various communities, not just physics, chemistry. We need help from material science people, organic chemistry people, device physics people, electrical engineers, mechanical engineers, fabrication, manufacturing guys. It's a problem which needs solutions from all the contributions. So this is the opportunities available for next 10 to 20 years, and it's good time to get into this field. Okay. So I have recently written a popular article on this EERI, the Energy and Resources Institute, which is based in New Delhi, and they come up with this Energy Future Quarterly, where we talked about the contribution of organic photovoltaics towards development of low-cost green solar cell technology. Okay, so in fact, I brought out all these informations and I just presented as a 4 to 5 page article, which is here. You may just contact me for the for this article, I can just share with you to read further. Otherwise, you can just Google it and you'll know everything about what I just said. Okay, so this is the kind of work we do in our lab. Our laboratory is ultrafast photophysics and photonics laboratory. We combine the knowledge of optics, spectroscopy, lasers. In fact, the initial my expertise lies in the femtosecond laser spectroscopy, transient absorption, photoluminescence spectroscopy, and nonlinear optics. Last 10 years, I started working on organic solar cells and other things. So we mix all these things to solve the various problems which I just explained just a few minutes back. Okay, so these are the various funding agencies which help me work more. Okay, and my workforce, I thank all the students who are there working. Unfortunately, due to this COVID, they all are gone home. But then once we come back and we assemble, we hope to do more good work. Okay, and just to not lose the track, I like to summarize this entire presentation where the main theme was to present demonstrate the virtual labs. Okay, yesterday I introduced you what is virtual labs and presented 3 experiments in the theme of modern physics. Today I presented an experiment based on laser beam divergence and spot size and 2 mechanics based experiments. And just now I just took a small detour to give a brief introduction of organic PVs. Again, I thank Professor Padma and the organizing team for the invitation, and I thank you all for your attention. Yeah, I'm done now. You may ask questions.
Thank you, sir. Thank you very much for your informative and more elaborative presentation in the 2 sessions. I hope all the participants have benefited from your presentations. So once again, I thank you, sir, for your support and cooperation you have extended in making it a successful one.
Thank you
Very much. So I request the participants to post your queries in the chat box. If you have any queries, you can please post it in the chat box.
One of the questions I've seen is I am unable to install Flash in Chrome. One of the participants, B. Nagarjuna, has asked. In fact, there is no alternative. That's what I mentioned yesterday in the beginning. Okay. So, but then it is not easy. It's easy to install Flash. I just showed you what to do. In fact, I do it every time I go. I need to keep clicking on various things to get to that point. Okay. So just do it. It should be there. Okay. Can we do the experiment wavelength calculation using laser, which you demonstrated using? You usually do it in your lab. Yes, you can do it. Yeah, you can do that wavelength calculation. It's once you have the formula, a formula would have set of knowns and unknowns. If you know a known, use the unknown. Use them to find the unknown. So that's how it is. Yes, I think this is all it is. Either I'm too fast and too bad to explain you, or if you don't have any doubts, or I'm really good at presenting. Anyway, thanks. Okay. Now, one more question I found. What is the effect of temperature on materials in modulation? Yes, temperature does have an effect because if you look at the rigidity modulation, it's not modulation, it is modulus. Okay, it's different from Nagarjuna. Rigidity modulus, if you look at it, it is dependent on length parameter. The moment you talk about length parameter, the length and everything that is related to length changes the temperature. And that's why the temperature starts affecting the material. Yeah. Future prospects of virtual laboratories. As long as COVID is there, there's a lot of interest in virtual laboratories. But then, as I said, don't simply get stuck to the COVID and post-COVID, pre-COVID problems. One can use these virtual labs to teach. They're meant for aiding the teachers, okay, and also the students. Once you generate interest in the students, they can do a lot of things. After certain age, we are stuck to our way of looking at it, and we are stuck to the textbook or something. Yeah, a student can really do more from his exuberance and things. So say that it's a strong prospect. Okay, yeah. I think I have answered what is available in the moment. Another question has come in. Okay. There's another question. What is this? Can you please repeat? Organic photovoltaics degrade bit due to photonic nature of periods. Do you expect enhanced lifetime of organic PV? Yes, this is where the opportunity lies. Okay, that's what I say. You need to do a lot to go from lab scale to the market. Okay, that's the opportunity. That's where we actually come in. I mean, that's why I said it's a good research field to get in now, because you can actually contribute for the success. Okay. Yeah, I think with this